All right, so we're going to talk about section 1.4 from the textbook, or linear equations is the topic of that chapter or the section. All right, so up until this point, you probably talked about linear equations before or linear something, but we want to dive deeper into the meaning and also talk about what they're useful for and some of the properties that linear equations hold. Linear equations are actually a very interesting kind of equation or function. We'll call them functions now. So before we were talking about equations, up in this now we'll talk about linear functions, which equation and function can kind of be interchanged, but functions have stricter conditions than an equation. An equation can be really anything, whereas functions have those stricter conditions of that x and y values correspondence. So linear equations are exactly what it sounds like. It's an equation of a line, right? Linear meaning a line. And linear generally refers to growing at kind of the same rate. They're linearly increasing. You'll hear people say that kind of terminology, which is really just saying that it grows at a consistent rate. They generally have this form ax plus by equals c. A, b, and c here are what we call constants, which are aka really numbers. Now, A, B, and C are, this little symbol here means element of. An element of is what we call in set theory is like a small piece, kind of. It refers to the giant set. So what this is just saying is that A, B, and C are numbers that are real numbers. And so remember, there's different kinds of number systems. And so real numbers are numbers that we can write that don't involve square root of -1, which is I. So this is the only thing that real numbers cannot exist with. So this, not real. We call those imaginary, and so that's the only condition that we have on the x, the a, b, and c, is that they have to be real numbers, not involving a negative under square root, and a and b have to both have a real value. One of them can be 0, but the other one cannot, so they both can't be 0 at the same time. We also know that the slope of linear equations is a consistent, and it's the same for the entire equation. So if we are given 2 points, we can always calculate the slope. The slope is the rate at which the linear equations increase or decrease. Slope means change. That's what that has to do. It is the change of how each point is increasing or decreasing depending on where you're traveling along that line. So let's suppose you're given 2 points. This is x1, y1. We use something called subscript notation, which is that x, and then this is the sub part. So I'll put a 1 there. That's the subscript, okay? There's also superscript, which is if you had like x, like the powers, exponents are usually like superscript kind of things. But for our case, we will have x sub 1, x sub 2. These are x values, but it's indicating that this is the first one, this is the second one. They're not the same. They're different, distinct values. Okay. Now, we have the formula that we can calculate, but before we talk about that, what slope is it is m. We use m to indicate slope, and why we use m is it's not really, we don't use s because s has a specific value in statistics and some other things, so we kind of don't use s, but they use m instead, and it's not quite clear where m comes from. There's various different opinions and stuff, but for our case, we just use m. So the top of the fraction, slope is always a rate. Rate indicates a fraction or a ratio. So whenever you see the word rate, think of a ratio, a percentage, something like that. So obviously, since we have a rate, we are going to have a fraction. And so this shows us a relationship between the y and the x. The numerator of our fraction for slope is going to be the change in the y direction. So we always calculate the change, how much change is going on, the distance between the y and the other y, the two y points we have for our coordinates, divided by the change in the x direction, which is the difference between those two x points. Now you need to calculate how much you're changing, how far are you going from the first point to the second point. So we use this change in the y direction over the change in the x direction. Obviously, we don't want to write this. In mathematics, everything is shorthand. We want to make sure that we can write most clearly without using a lot of words. So we write these little triangles, shapes. These are what is called delta from Greek alphabet. And so we use this delta character to indicate change. Delta always refers to change. So we have a change in the y and a change in the x. That's what we have there. So we call that the change. And we can't have x1 and x1 equaling x2 because that'll give us a 0 in the denominator, which is an undefined value, which implies that it's not a function also. So we want to be careful with that. Now, obviously, we will also have some cases where possibly this can happen, but we'll have a specific kind of idea of what goes on when that happens. All right, so m is going to be that delta y over delta x that we have. And so now we want to derive how we actually calculate the slope. And so if we're calculating a change in the y direction, we need to figure out what we're going to calculate. So let's say that we have a line here, and we have, here is our points. So we have, here is our y values. This is y1 and this is y2. Here's our x1 value and our x2 value. So in the y direction, we want to calculate this distance here between these 2 points. That's basically the distance we're calculating. And so if we look at here, we need to calculate the difference between y2 and y1. So y2 minus y1, because that will give us this value here. Because remember, if we take, use a different color here, if we take y2, the distance between y2 and the origin, everything is with respect to the origin, or 0, 0, this y2 here is this long distance. If we subtract away the y1, that's this distance, we're left with this difference distance there. So that's why we want to do that way. So then we can also do the same idea. So we take x2 minus x1. And so that's how we calculate the slope for a linear equation, is we calculate this x and y kind of idea. Now, I did mention that we don't really want to use the idea of having we want to use the functional notation, because in Precalculus we're getting you prepared for using functions instead of just normal equations that we have been seeing, which is fine. But what we want to do instead is we want to make sure that we can rewrite it later on. So we'll leave this like this for now, but we're going to come back to this and rewrite it with using functional notation. Okay, so let's talk about the different kinds of slopes that we will have, because there are 3 different kinds of cases. So once we have our general form of an equation, of our linear equation, so I'll just write that up here so we can remember our ax plus by equals c. Once we have this, we are going to want to classify this into 3 different cases. Because remember I said that a and b can't both be 0, but I never specified what happened when a is 0, b is a value, or when b is 0 and a is a value, or when both are values. So that's kind of when we're going to classify this into 3 different cases. So we break it down by cases. So the first case that we'll have is when a is not 0 and b is not 0. So both of them are numbers. So we will have an actual equation it's going to be a slanted line depending on the way that the slope is. So if the slope is positive, it's going to grow like this. So it grows in a positive manner. Now, if the slope is negative, it's going to decrease from left to right. So usually we always refer to graphs as reading them from left to right. We never read them right to left. Always read left to right, from the bottom to the top. That's the way that we generally read graphs. So this is a positive increase, this is the negative decrease, and that's what the slope has to do. So there's a negative there. All right, so that's the first case, and we've seen those before. You've graphed them before. Case 2 is a horizontal line, and it occurs when a is 0, which means that you just have an equation in the form y equals some value. Now this should make sense because y is going to be consistent value, and it's going to be in wherever y is. So if we have example y equals 5, well, I look at my graph, I go up 5 places, and I'm just going to have my horizontal line at y equals 5. That's what I have. Same thing with if y was to be negative 5. Instead of being up, it's going to be down. It's going to be down here. So that's the same idea. It just occurs when you have y equals and then some number. It's a horizontal line just going through the point where y is that number. It's all those points where y is that number. Okay, and then the last case that we have is a vertical line, and you can imagine that is when x is some number, and the slope is going to be undefined. The slope for the horizontal line was always 0. It's going to be always 0 because what's happening is your y values are going to be the same. So if you're subtracting y1 minus y1 because they are the same, it doesn't matter what's going on in the denominator because the top is always going to be 0. So that implies that the whole thing will just be 0. Now, vertical lines are a little different because the x1 value is the same as the x2 value because you're given x equals, say, 5. This is going to be the same for every single point on the line. Now, remember our slope formula is y2 minus y1. Well, the denominator is x2 minus x1, but we know that they are the same, which implies that it's 0 down there. And when you divide by 0, that's going to be an undefined slope. So you want to make sure that you be careful with that one as well. All right, so now the next thing we want to talk about is slope-intercept form. And this is going to be a form of a linear equation that we can generalize and use. So we have y equals mx plus b, where m is the slope and b is our intercept. All right, that is what that is. So the next thing that we're going to want to do is talk about what happens when we want to write this in functional notation. So we have f of x equals mx plus b. Remember, y is written generally the same way as f of x. Y is equal to f of x in these cases. So the next thing we can do is substitute for this one. We want to graph this f of x equals x plus 5. So we will draw our graph here. And whenever you're asked to graph something, I generally like to just make a t-chart, so f and f of x, or this is y, x and y, and start plugging in values. So first thing, let's plug in 0 for x, so that's f of 0 equals 0 plus 5, and that should make sense because that was our intercept. And now let's plug in a negative value since we have that plus 5, so f of negative 1 equals negative 1 plus 5, which equals 4. So now I can plot these 2 points. I have 0, 5, and negative 1, 4, and I connect them together, and there's my line. So that's all you have to do when you're graphing. All right, so the next thing that we want to talk about is average rates of change. So linear functions have a constant slope. They're one of the only functions to have this. calculus is the study of change and predictions. So if we want to calculate the slope of other functions, so for example, the parabola, the square root function, a cube function, cube root function, all those kinds of functions, we would have to do something else because we don't have nice formulas. We don't have nice formulas for calculating slope of these other functions. We don't have that. So we need to derive or calculate something else. There is some things that we can do is calculate the average rate of change between an interval. So at this point in the class in precalculus, calculus is when you can calculate slopes of any function that you can use. And slopes are very important in the world of calculating speed, velocity, acceleration, position, that kind of stuff. It's very important. It's also important for growth rates in bacteria, all kinds of stuff like that. Those are some applications that you'll see in calculus. But calculus, like I said, is the study of change in predictions. We can't calculate all those predictions yet. So what we have to do is just be able to do a little tiny snapshot of calculating some change. So what we will want to do is calculate the average rate of change. Now, whenever you introduce an average, there's always a margin of error because we are averaging things together, so we're not able to exactly predict like the exact change that's going on. We'd have to do a lot of different things. But this is the definition from the textbook explaining some information about functions and average rates of change. So if we have a function, we'll call it f of x, and here's the function that I drew here in the blue. It's defined on an interval x1 to x2. So this is our interval from, let me use red, from here to here is going to be my interval, where the red is. So that's x1 to x2, and we include those endpoints. The average rate of change that the function is that's happening with that function is going to be the slope of what we call the secant line between those 2 points. This is a lot of terminology, right? A lot of things going on. But all that we need to do is realize, all right, if we calculate the average rate of change in an interval, we take the 2 endpoints of that interval, calculate out the points, calculate out the slope there, and then that's going to be our average rate of change for the function in that interval. That is what we are doing. That is essentially what we're doing. It's the slope of the line passing through those points, which we call that line the secant line. So back to our average rate of change, or our slope formula. So remember, this was slope. Delta y over delta x, which is the change in the y direction over the change in the x direction, is going to be the difference of y's over the difference of x's. Now remember, I said I didn't want to use y's anymore. We don't want to use that because we don't want y anymore, because we want strictly f of x in functional notation. But remember, I told you that y is the same thing as f of x, that we want to write it like this. In this case, it's the same thing. Does it always mean the same thing? Not quite, but for our cases, it's going to be the same thing. So if I have y2, this is going to imply f of x2. That's what that means. We're just keeping the same subscripts. So we can replace these, the y2 with f of x2, and the y1 with f of x1. Now, that is how we get our average rate of change. This is our slope formula for functions. Instead of using y's, we use f of x's. All right, so now we want to, let's do an example. We want to use slope-intercept form to write an equation for the following information, and we want to write it in functional notation. That's our goal. So that's what we want to do. All right, so the first thing that we're going to do is we have 2 sets of points. So let's calculate and write an equation. So we know we want it in the y equals mx plus b form, and I'm going to write it like this, and at the end we'll write it as f of x. We'll write it as that at the end. All right, so the first thing that we're going to do is let's calculate our slope. So m equals the difference of y's over the difference of x's. So we'll call this y1, and this is y2, x2, x1. So we have y2 minus y1 all over x2 minus x1, which is y2 is going to be negative 2 minus 5 all over x2 is 1 minus 4. That's what we have. You got to be very careful with the negatives here, because if you don't, you will make a mistake and get something wrong. So this is going to give me negative 7 over 1 plus 4, which is 5. So I have negative 7 fifths is going to be my slope. All right, now, sure, y2, okay. So now what we're going to want to do is substitute this into our y equals mx plus b. And we want to substitute this in, so we get y equals negative 7 fifths plus x plus b. All right, now what we need to do is solve for b. We need b. Now, where do we get the x and y values? Well, we already have them from one of our pairs of coordinates. So I'm going to use 1 comma negative 2, because I think that should be our easiest one. So I get negative 2 equals negative 7 fifths times 1 plus b, and I'm going to solve for b. So I get negative 2 plus 7 over 5 equals b. I'm just adding this fraction here to the other side. Now I need to convert negative 2 into something in terms of fifths, so that's negative 10 over 5 plus 7 over 5 equals b. b is going to be negative 3 fifths. So my final, or my function, or my equation that I'm interested in is negative 7 fifths x plus minus 3 fifths. Now, I wasn't asked to leave this like this. I need to use functional notation. So we do a swap for the y. So I get negative 7 fifths x minus 3 fifths. So that's going to be my solution for this type of problem. All right, let's move on to our next example. We have this graph here, and we're asked a few different questions of this graph. So we're asked to find the average rate of change of the temperature between March and May for the first one. So A, average rate between March and May. All right, so let's find out March. So March is point. So if we look at the graph, it has the temperature in the y direction. So from 0 to 9, it looks like 90 degrees-ish. And then the months of the year are down here. 1 represents January. So January, February, March is going to be 3. So 3, that's going to be March. So we have January, February, March is going to be this value here. So March is going to be 3,38. All right, let's find May. May is going to be the 5th month. January, February, March, April, May is going to be 5. So that's going to be 5,60. And these are the average temperatures for somewhere in the United States, I believe, is what we are interested in. So we're asked questions about this Odessa town somewhere, or yeah, some place, and these are the average temperatures that we have. All right, so this is going to be March's temperatures relation. So this is the month, this is the average temperature, month, average temperature, this 5 and the 60. Now we need to calculate the average rate of change. How much averagely, what's the average that is changing between those two values? So this is my x, this is my x, this is my f of x, this is my f of x. So remember, our slope calculation is the change in y over the change of x, which is f of x2 minus f of x1 all over x2 minus x1. So f of x2, this is going to be my second point. So we have 2, we have 1. This is f of x2, 60 minus 38 all over 5 minus 3. That's going to be the difference that I have. And you might ask why. Remember, this is f of x2. This is f of x2. This is x2. This is x1, and this is f of x1. All right, so 60 minus 38 gives me 22, divided by 2 gives me 11. So the average temperature that is changing between those 2 points is 11. It's changing 11 degrees. Okay, so that's the answer to first one. So we have 11 degrees. Now we need to find the average rate of change between September and November. So September, November. So let's find September. September is month 9. November is month 11. So that's these 2 points we have. Now look at the graph though. We can see that it's kind of decreasing, which makes sense, right? Because the hottest months are July and August, and then it kind of starts decreasing because it gets into the winter seasons again. So we have September, which is 963, and we have 1142. 42. All right, so now we're going to use the same formula from above. So we have f of, this is going to be f of x2. It's going to be f of x1. So we have 42 minus 63, all divided by 11 minus 9. Now again, you could do this the other way. It does not really matter. You just have to be very careful with the signs, and you have to stay consistent. So we have negative 21 divided by 2. And so this doesn't really simplify nicely, so we'll just leave this. Negative 21 over 2 is going to be the rate. 21 over 2, negative, and it makes sense that it's decreasing, right? That negative is implying a decrease. And if we want to do this as a decimal, this is 10.5, so it's decreasing in a negative 10.5 temperature degrees. That's how it's decreasing. Okay, now we're not given a graph for this example. The last example we want to do, we want to find the average rate of change for the function, this function, square root, between all these intervals. So I have 3 intervals that we want to calculate. Now we're not given ordered pairs, we're just given an interval. That's it. So for the first one, so when you're not given a graph or the points, you have to get the points yourself. So this is going to be x1, this is x2. So let's create our ordered pair. So we have x1. We need f of x1. We need f of x1. So we have negative 2, comma. If we evaluate f of negative 2, we get square root. We plug in negative 2 plus 3. That gives me a square root of 1, which is just 1. All right, that's good. Now we need to calculate f of 1, which is square root of 1 plus 3, which is square root 4, which is 2. So f of x2, comma f of x2, or x2, comma f of x2, is going to be 1, comma 2. So these are the 2 points that we're going to want to use for our formula. Let me just move this one here. We'll move this one down. Okay, so now we need to use our formula, change in the f of x direction. We can rewrite over the change of x. That's exactly what we're having, the change in the f of x, which is the y, and over the change of x. So we have f of x1, f of x2 minus f of x1, all over x2 minus x1, which gives me f of x2 we know is 2, minus 1, f of x1 is 1, so that's this value. So let me write these. So 2 minus 1, that's this value and this value. Now we're going to switch back, and I'm going to calculate x2, 1, negative 2, minus 2, which gives me 1 over 3. So it's increasing averagely by 1/3 in that interval, which means that the distance between the points in that interval is 1/3. So on average, the distance is 1/3. Now again, this doesn't mean that every single one is increasing by 1/3. This just means the averages, which means some of them might be increasing by 1. Some may be increasing by 2, 2/3, negative something, like it all averages out to just be 1/3. And that's as good as we can estimate and calculate it in this class. And we'll actually be able to calculate something later on, I believe. But for now, this is what we want to do. All right, so let's calculate the distance in the interval 1 to 6. So we need to do the same thing. So we have our first one, x1 comma f of x1. That's the point we're looking for. And we're looking for x2 comma f of x2. So we know this is 1, and this is going to be f of 1. But we need to find out what 1 is. And so f of 1 is going to be, we already calculated that out earlier from here, but that's going to be 2. So we can see it's from here. This is the f of 1. So my pair is 1 comma 2. And now we want to calculate 6. So we get 6 comma f of 6. So that's 6 comma f of 6 we did not calculate. So we need to calculate f of 6 equals square root 6 plus 3. So we have equals square root 9 equals 3. So we have 6 comma 3. Okay, so these are our coordinates that we have. So now we can calculate our slope, which is the change of f of x over the change of x or change of y. So we have f of x2 minus f of x1 all over x2 minus x1 equals f of x2 is going to be, let's use our colors. So f of x2 is going to be 3 minus 2. Here's our other value. And then we need to calculate all over x2, which is 6, minus 1. So I get 1 over 5. So that's the average rate of change between that interval. Notice that they are different, and that's to be expected, because if they were the same, then you might have to start asking questions about, well, is this the same function? Now, this isn't to say that there isn't intervals where the slope is, or the average rate of change is the same, but in this interval, it's way different, it's bigger than the other one, right? And so we just want to be careful. All right, and then the last one that we have is 10 to 20. And so let's just remember f of x is square root x plus 3. All right, so we need to calculate f of, so we have 10 here. We need f of 10. F of 10 equals square root 10 plus 3, square root 13. We can't do anything with that, so we're going to leave it. Now we need to calculate f of 20. That gives me square root 20 plus 3, which gives me square root 23. So my other pair is 20 comma square root 23. There's nothing I can do with these values. It just has to, we just have to keep it. All right, now let's use our formula to calculate the difference and the change. So the change in the f of x and the x direction. So f of x is going to be our square root 23 minus square root 13 all over 20 minus 10. So we get square root 23 minus square root 13 all over 10. Okay, we cannot combine the square roots because their base underneath the radicals are different. We cannot simplify them. They're both prime numbers. So we will leave it like this. Do not combine them to be, don't subtract under the radicals. That's wrong. Don't do that. This is your final answer for solving these kinds of problems. So it's okay if you get radicals, because we're not using calculators in this class, so we're not going to get a approximation. We're going to leave it, this is the exact solution. So we'll leave it like this. You would leave it as the answer. That's it.